Okay, now I'm going to share the screen. Oh, hold on. Ah, trying to do 8 things at once. So I'm looking at number 9, for example, and we have this function ln 7 minus x, and we want to find the power series. There's actually a couple ways to do this. I'll show you a couple ways, um, but I'll also show you there's kind of a brute force way, and then there's also an elegant way. So let's take a look at both. So I'm going to go and change my camera here. Get this pinned. The ln of 1 plus x is, well, let me back up here. Oh, you know what? Let me just go up even a level here. Just the function 1 over 1 plus x. That's an alternating series. Um, it's 1, I remember this. No, it's actually not alternating. Oh, hold on. No, wait a minute. It is. It's 1 minus x squared minus x cubed plus x to the fourth minus x to the 5. And the idea is that this formula here, even if I go up in the general formula, it's 1 over 1 minus r. You might remember that from uh, other classes. You get 1 plus r squared plus r cubed. So this little formula here is kind of nifty because if I integrate it, this turns into ln 1 plus x, and then these guys just integrate using the power rule. I'll write out a few terms. Something like that, right? And this is true. This converges only for x between -1 and 1. So the same is true here. This is only true for that interval. And so I'm going to turn this thing into this thing. And so what we need to do, we need to get a 1 where the 7 is. So let's factor out a 7. And then I need to get a plus sign where that minus sign is. So I can split up. This is ln 7, and then because I have a product here to split up as 2 ln's. And what I'm going to do here is write it like this. It looks a little awkward, but it'll help with the setup. You all see that?
Yep.
So then, um, right here, we're going to use kind of this form here and adapt it for here. So you'll notice that what I have here is the same as what I have here, except that I have a negative x over 7. So what I'm going to do then is well, I just need to adapt it. Let's see. So this ln 7 in front doesn't really do anything. Everywhere I have an x, I'm going to put a negative x over 7. So it's going to be negative x over 7. And it looks like the negative will cancel because it'll square away. So that'll be x over 49 and a 1 half. So it gets a little, give me a moment here. You know what? Let me write it out just kind of generically. I'll write out a few terms. Oops, that's minus sign. That would be the series. Okay, y'all see what I did there? I took this generic form, I adapted it to here. You know, everywhere I had an x, I put a negative x over 7. And so it looks like all the terms are going to be negative. Interesting. this will be, this negative will square away. This will be 49, so I'll have, this negative stays less. I'll have 1 over 98 x squared. This negative will actually stay. I have 7 cubed times 3. I'm just going to poke that in my calculator. Looks like it's going to be this 1 over 1029 x cubed. And I'll do this one more last one. This negative will square away, but this one will, or fourth away, but this one will stay. I have 7 to the fourth times 4. It's 9604. And that should be my series. And the only adaptation I make here is I have to just also look at this negative x over 7 and adapt it for the region of convergence. Interesting, when I take the negative, when I negate all the sides, that's just simply, well, I'll do it. It reverses the inequality, but it still works out. And if I multiply 3 by 7, actually, I'm just going to write it the traditional way. That should be my interval of convergence. Does that make sense?
When you put the natural log of 1 plus x, like that spelled out, makes that probably 100 times easier than the way that the like get help showed you to do it.
Oh, really?
Yeah.
I didn't look at it. um, yeah, you know what? If you guys don't mind, I'm going to show you something here. I'm going to go to Desmos. I'll share my screen here in a second. Let me get Desmos going. One way to check these series are the same is to actually graph them. And for some reason, okay, there we go. It's not loading. Give me a second here. Yeah, it's for some reason my Desmos is not loading up. So I'm going to try. Oh, there we go. It's going real slow. All right. Finally got it to work. I'm going to graph. Give me a second here. So I'm going to share my screen. So there's the graph of ln 7 minus x. And then what I'm going to do next is I'm going to graph the function I just found. And that's actually pretty good. Let me do one more term. Yeah, that's looking pretty good. Can you guys see the conformation? Do you see that happening right here?
Yeah, in the
Yes.
videos, they that was really helpful when they were doing that with the original power series too, because
Yeah,
it gives you a very quick way to check your answers.
it's a good way to check. Yeah. It's going to converge between -7 and 7. You'll notice you have a vertical asymptote at 7. So this blue graph is eventually going to probably have to get really close. And then back here at -7. So all the convergence will be happening between -7 and 7. You'll just get better and better conformation. So if I add, I'll do one more term since I got it entered in. Oops. Yeah, you see a little more conformation. All right. I'll go ahead and stop this. The only other way that I would do this is, to use the general formula. I don't know if I wouldn't recommend it necessarily. Let me just show it to you. The general formula is to let me just recall what you have C naught plus C1 x plus C2 x squared plus C3 x cubed plus C4 x to the fourth, where the Cn is the nth derivative of the function. In this case, it's going to be centered at 0 over n factorial. This is just brute force. And what the unfortunate thing here is that you're going to have to take the ln function. You're going to have to take a whole bunch of derivatives. That's not that hard to do, but it gets kind of tedious. And this would be -1 over 7 minus x squared. F, the third derivative would be, it's going to be 2 over 7 minus x cubed. I'll do one more. Fourth derivative will be -6 over 7 minus x to the fourth. And then you have to plug in 0. So you get f of 0 is ln 7, f of 1, I'm sorry, f prime of 0 is 1 over 7, f double prime of 0 is, you'll see set -1 over 49. F triple prime at 0 is 7 cubed. That's going to be 2 over, I forget what that number is. 7 cubed is 343. And then at the fourth derivative, it's going to be -6. That's 7 to the fourth, 2401. Okay. And then to add fun, you have to put them into this formula here. So C naught is just going to be f of 0. That's just going to be ln 7. C1 is going to be f prime of 0. It's going to be 1 over 7 divided by 1 factorial, which is just 1. C2 is going to be, um, oh, you know what? I have a minus. I forgot. Oh, I got really easy to fix. This should be minus plus minus. I forgot the chain rule. So that makes this that. There we go. Okay, so that'll make this a minus. So C sub 2 is the 1 over 49, but then I have to divide by 2 factorial, which is 2, so that's 1 over 98. And that minus sign, did I mess this up? I think I might have, I think they might all be negative. Yeah, they should. All right, anyway, let me do one more. C sub 3 is the -2 over 343 divided by 3 factorial, which is 6. So that's -3. So 343 times 6 is 2058. So I have -2 over 2058. And lo and behold, that's actually 1029. So it's working out. Oops, my bad. And so I'm generating the coefficients brute force. You can see them kind of being generated here. And I think I have a minus sign issue. When I take the derivative here, okay, that minus, now I take the derivative again. Actually, I was right. The minus sign always appears. That's darn. So yeah, that'll be negative. So I was able to generate the coefficients, the brute force method. Um, I don't know. You take your choice. Which one did you like better?
I like the first one better for sure.
Okay. Um,
There's more there in the second one.
Let me go back to infinity here. So anytime you get like, I'll share the screen here. Like number 7. Oh gosh, I didn't mean to do that. You have ln of 1 plus 15x. You could do it the same way. Um, it's got a 1. It's in fact, oh, let me get my screen going. So the ln of 1 plus 15x, that's actually probably a little easier because you just simply, it already kind of fits the form. You just have a 15x wherever you have an x. So everywhere you have an x, just put a 15x. And then just work out what the numbers are. That one works out pretty good because it's already got the form. It's got a 1, it's got a plus sign. Okay. And then I was going to show you the arctangent. I'll share the screen again. Because the arctangent falls into this kind of category here. The number 10 down here at the bottom, it's arctan of x over 15. Now you could work that out the long brute force way, but man, you're going to be taking derivatives. That's just going to take so long. So I'll do it the same way. The idea is that I take the generic form, which is 1 over 1. Well, I'll do 1 plus x, so that's the alternating series, 1 minus x plus x squared. Let's take away x cubed plus x to the fourth, take away x5, etc. And then what I do, normally if I replace x with x squared, that makes all these powers double. And then when I integrate, I have a generic formula for the arctangent. And I get x minus 1/3 x cubed plus 1/5 x to the 5. Take away 1/7 x to the 7th plus 1/9 x to the 9. Take away 1/11 x to the 11th, etc. Now, the only adaptation, if I want x over 15, would be to kind of come down here. Well, actually, I got it already going. It's just replace all the x's with x over 15s. This is going to converge real fast because we got such a big power here, but it's going to have a very narrow region of convergence, and that's probably good enough. But if you wanted to work it out, just get a few numbers. Um, 15 cubed is 3375 times 3. So if I show you it all, it's going to be x over 15, and then it's going to be 1 over 10, 125, x to the third. I'll do a couple more. Geez, yeah, the numbers get huge. It's going to be 1 over 3, 796, 875, x to the 5, yeah, etc. All right, but you see it. That's actually that would be the first few terms of the arctangent of this particular function. And again, you can check by graphing them. You can put this function into Desmos and then draw a few terms. And if you see that conformation, that tells you you did it right.
But in Desmos, if we leave it in the original form rather than expanding it, like if we put 1/3 and then put the parentheses x
That
over
should work.
15 to the third, it'll take it that way too, so
Yes,
that we don't have so many keystrokes.
that is true. Um, it may be the case if I look at the question. Um, Actually, it seems like it's pretty open-ended too on Infinity. It seems like if you enter it, the way it seems like if you enter it the way I have it here, in this row, it should be acceptable.
Yeah, I went back and forth with mine because some of them, like I could do them in my head. So I just put the number down there. But once it got so big that I was going to have to grab a calculator, I put it in the other form and it still took it.
Okay. Um, oh, one more thing about the radius of convergence. This is true for x between -1 and 1. And when x squared is a little weird because that reduces, takes away the negatives, but I'm going to keep it. I'd rather play it safe. It's going to be like that. So if I multiply by 15, that should give me that. You can check it on your by Desmos. So I'll just say check on Desmos. And to be honest with you, on this chapter 8 quiz, um, you can go ahead and use Desmos. Why not? It's a good program. All right. Any last questions on these? These are the ones from 8-6. Any last questions?
Trying to look at all of them.
So 8-4, number 9. Here we go. Apply the ratio test to determine convergence or divergence, or state that the ratio test is inconclusive. You have limit then goes to infinity of the quotient of successive terms. Let's find out. All right, so the series is from 1 to infinity e to the n over n factorial. And I will, come on. So what I do is I set up a quotient of successive terms. Now, in this case, the absolute values are not really necessary because these are always positive, but I'll go ahead and put them in there at least that first time. So I get that. I get e to the n plus 1 over n plus 1 factorial divided by quantity e to the n over n factorial. That flips over the bottom fraction. So I have e to the n plus 1 over n plus 1 factorial. This n factorial will actually move to the top. This e to the n will stay in the bottom. And then I can do some reduction here. The this e to the n will take out all of the e to the n's except for a single one of them. This, in other words, the top has one more e than the bottom, so that an e stays behind. And then n factorial takes out, if you'll notice that n plus 1 factorial is actually n factorial times n plus 1. So what ends up happening is you get e on top, n plus 1 on the bottom. Okay, after all this reduction. And then you got to take the limit as n goes to infinity. And the e stays e, the n, this obviously goes toward infinity, so this thing goes towards 0. And so this is good news. This tells us that, well, it's less than 1. So if the ratio test gives you a quantity that's less than 1, the series converges. Okay. It doesn't converge to 0. So don't confuse the limit here as the convergent value of the series. It just simply tells you that the series is convergent. What this converges to, I don't know. But it doesn't converge to 0. In fact, these will be positive quantities. That's, I think, all we wanted to do on that one. I think that was yeah, we just select, uh, in this case, convergent. And, I'll say this in general, the ratio test is pretty handy when you have a combination of exponentials and factorials. I'm going to go back to the infinities. I'm going to go back to the screen. So like on number 9, it worked out just nice. But on number 10, I don't think it's going to work because when you do the ratio test, you're actually going to get common powers on both the top and the bottom, and you'll end up getting 1. Okay. when you on number 10 where you have strictly a basically polynomial quantities here, you do the best thing to do here would be a comparison test or a p-series test. And usually when you have uh, powers like n to the first and n to the seventh, you're basically like that would just ignore the five. After a while, the five becomes negligible. This would be similar to the series 1 over n to the sixth, and that would converge. It would actually converge anything, 1 over n to anything converges as long as the power is greater than 1. So 1 over n squared converges, series 1 over n cubed converges, and so on. But the series 1 over n, which is the harmonic series, actually diverges. So you would discover on number 10 that the ratio test will not get you anywhere. The ratio test will actually equal 1. And that doesn't help you any. So live and learn.
So for
Number
those, we won't have to find the limit of the series, or we won't.
No,
Okay,
you just
we're
need to
just
show whether it's convergent or divergent.
okay.
Most of these, you're not going to be able to determine the limit exactly. At best, you could write out a whole bunch of terms, add them up, and get an approximate value. Something like Excel would, eat this up because you can just type it in a cell and then just, copy paste and then just create like 100 rows. Um, like number 8, ratio tests should work out really nice because you've got a combination of factorials, exponentials, and polynomial. So when you have like a kind of a mix of them, like number 7, yeah, I think ratio test is the way to go because you've got exponential and polynomial. 6, yeah, ratio test because you've got polynomial on top, factorial on the bottom. And 5, it looks like a nightmare, but you know what? It's probably going to work out pretty good. If you do ratio test, you've got polynomial and exponential. I think this will work out. Your ratio test should work out. It's going to look messy, but it should clean up real nicely. Number 4, ratio test probably won't work because you've got n to the 1 and n squared. In fact, this kind of falls into the class of being similar to just 1 over n. Now this has a blinker on it. This negative 1 to the n, it makes it an alternating. So, but 1 over n series diverges. With the blinker on it, it converges, but it converges conditionally. So I think they don't think they're asking you that here. They just want to know whether it converges or diverges. So it looks like this is all ratio test. All right. Did that help? Who was that, Charles? Was that yours?
Yeah, that was me. But actually, the problem that I got on for that one for number 9, because I'm like, that didn't seem like what I got. It was e to the n over n to the n, and that's what kind of
All right, we'll take a look at that one.
threw me for a loop because it was, I forget what. Yeah, because it ends
Let's
up with
try
a.
it out.
Okay.
I'll try it with ratio test. So I'm going to e to the n plus 1 over n plus 1 to the n plus 1. And I'm just going to skip a step, divided by this, which just flips to n to the n, e to the n. I'll just do some algebra. All of these e's take out all but one of these e's, so I have just an e. It gets a little weird here because I have n plus 1 to the n plus 1. If I write n plus 1 to the n plus 1 is n plus 1 to the n, and then I have an extra n plus 1, then I'm going to have an n plus 1. And then actually, I'm going to take these two guys, n over n plus 1 to the n. And, oh, this gets weird. You see what I just did there? I took
Yeah.
this and this. Now this, you got to be careful here. This actually, this should actually converge to an E. This is one of those weird.
Yeah, that's what kind of threw me for a loop because I found the answer, but the help that I got was like n over n plus 1 to the n converges to a famous
Yeah,
value, and I'm like, I don't know that famous value, my guy. Like, I need help figuring out how I would get there.
it's actually, yeah, n plus 1 over n to the n is what you see there. And this is how E is defined a lot of times. But I
Okay.
have it flipped over. So what we can do is we can flip it back over, make this a negative n. So that would be n plus 1 to the n to the negative n, which is going to give us e to the negative 1. So you know what ends up happening is this thing becomes e to the negative 1, and the e's cancel. How about that? So you have 1 over n plus 1,
Which
and
is zero.
which converges. So when you put the limb on there, when you when you put the limb on there, as n goes to infinity, yes, I've been keeping off the limb until the end, and then yeah, it's going to be convergent.
All right.
So I should have a series thingy on there.
But just keep my eye out for that alternate value of E, or alternate of E in that case.
You know, you could almost just get away with just recognizing that this is finite.
I got you.
It doesn't matter if it's a billion. If it's finite, something over n plus 1, this is eventually going to overwhelm it. So this could be a humongous number, but this is still going to go to 0.
Okay.
So yeah, I don't think most people walk around knowing that particular one by heart, but
Okay, I was making sure it wasn't just me. That sounds good. But I mean, if we
yeah,
look at it, if one term goes to 0, then that's going to multiply by whatever else, and it'll be 0 regardless, right?
say it again.
So like the E over n plus 1, or the n plus 1 there, that's going to go to 0 on the limit. So we know that that's going to equal 0, and multiplied by whatever else would be 0, right?
You got to be a little careful with that, because you can have kind of competing limits here. Limits are a little tricky. This first part might go to 0, but we don't know how fast this thing converges. So I wouldn't rely on that. You can get yourself in trouble doing that. The best thing to do is just try to algebraically reduce things down as far as you can go before you take the limb. Try to get it as simplified as possible. And then you should be confident by taking the limb. Otherwise, limbs don't behave always as you expect. This is a good example right here. This one is, if you look at the inside, it's actually going toward 1. And you have an infinity on the outside. And you say to yourself, well, 1 raised to any power is, 1. Well, this is not quite 1. That's the problem. You have like these competing growths. And do they shoot off to infinity? Do they shoot off to 0? Or do they shoot off to somewhere in the middle? And interestingly, this one actually trends toward e to the negative 1.
Okay.
But you may not know that, and that's not really, you don't have to know that, as long as you just recognize that this is going to be finite. Because ultimately, this thing will just make it go to 0 anyway.
Okay.
So I'm going to share H7. Right, like number 11, is that one you're looking at?
Yeah.
Or
Yes, like that.
Okay. Yeah, I'm looking at that one. We may just have to brute force it. Yeah, I don't know if there's a quick and easy shortcut. Not like the ones we did previously. With square roots, well, let me just write it down. We've got f of x is rad 100 plus x. And we just want to figure out some coefficients here. We'll just kind of beat it up with a stick, I guess. The general form is the coefficient c sub n is f to the nth derivative of f evaluated at the center over n factorial. Here, in this case, the center is going to be 0. So what I need to do is work out a whole bunch of derivatives. Now, the function itself is considered the 0th derivative. The first derivative, let's see, it's going to be 1 over 2 radical 100 plus x squared. I'm sorry, no, that's radical 100 plus x. And then the chain will just give me a 1. Let's do a couple more. Gotta be a little careful here. It's the second derivative. I'm going to write this temporary. It's 1/2 100 plus x to the negative 1/2. So it's going to be negative a fourth 100 plus x to the negative 3 halves. So I don't know. Sometimes you look for a pattern. Sometimes a pattern will become evident. So the third derivative, maybe I'll just keep them in this fashion. So we get 3 over 8, 100 plus x to the negative 5 halves. Let's do the fourth derivative. It's going to be negative 15 sixteenths. Come on, pen. Oh no, I was running out of ink. Ah, darn it. So, all righty. So now I plug in 0. The original function just gives me square root of 100, which is 10. The first derivative at 0 right here is going to be 1 over 2. So it looks like we're going to get square root of 100 each time. So that's 10. So I actually have 1 over 20. Second derivative at 0 right here, that's going to make, I got to be a little careful here. Oh, actually, it's right here. I have it. So that's going to be 10. So it's going to be 10 to the third power. That's going to be negative 1 over 4,000. Let's do a couple more. Third derivative. So it's 3 over 8, 100 plus x to the 5 halves. So square root of 100 is 10. 10 to the 5 is 10,000. No, 100,000. So that's 3 over 800,000. That's getting big fast. Here I'm going to have, oh man, I'm going to have 10 to the 7th. That's 10 million. So I'm going to have negative 15 on top. 16 times 10 million is 160 million. How about that? Okay, crazy. So then it appears now to add to the fun, you have to divide each of these by n factorial. So when you divide by 0 and 1 factorial, you get no change. When you divide by 2 factorial, you're dividing by 2, so that's actually negative 1 over 8,000. When you divide by 3 factorial, that's 6, but 3 over 6 is 2, so this is actually 1 over 1,600,000. 4 factorial is going to be 24. Geez. This just gets nasty. I can maybe get a value out of that. I don't think it's going to be worth the trouble to reduce it. Nah, my calculator even choked on it. So it's just going to be a crazy big number. So 24 times 160 million. Okay. And that should generate our series. I think that's what it wanted. That was number, it only wanted up to 3. Man, maybe do that extra work. All right, I don't need all that extra. So it looks like C naught will be 10, C1 will be 120, 1 over 20. C sub 2 will be negative 1 over 8,000. C sub 3 will be 1 over 1,600,000. And then you're supposed to find the absolute value of the error in approximating rad 101. Oh, geez. You know what? I never actually even covered that in my lectures. Literally, you type it in your calculator. Yeah, that is the correct answer. So I did get the correct answer. I feel good about that. I forget who asked this question. Was this,
I did.
does this
Eric.
help?
Yeah, I haven't gotten to that yet. I saw them and they looked very hairy. And so I was like, while we have you, because the homework's not due until the day of the quiz, I just wanted to see one of them worked out.
Oh,
That
sure.
that did that did help. When it says divided by 0 factorial, we're not really doing that, right? Because if you divide it by 0, it would be undefined. So
No,
we just
zero factorial is actually 1.
oh,
Factorial is an
okay.
interesting beast.
Okay,
Um,
so it's like an exponent to a 0 power, it just turns into 1.
right. The definition of factorial for integers is just to take the product of all the numbers from n on down to 1.
Yeah, I know how
However,
to do the rest of them. I just never knew that 0 factorial was 1.
right, 0 factorial is defined differently. It's actually mostly at this level, it's defined by, I would call it reverse justification. We talk about factorial actually comes up when we talk about permuting objects. How many orderings are there of an object? Now, if you have 0 objects, you could argue that there's one way to order nothing, which is to leave it alone. I find that to be kind of unsatisfactory. It turns out that there is a way to do it called the gamma function. You don't have to do this for this class, but if you're ever curious, type it in. The gamma function is actually a continuous function, which actually acts like for positive values, it actually acts like the factorial for any x. It doesn't have to be an integer. So if you type in 1.7 into the gamma function, it'll give you a value. It's very interesting.
Hmm.
So something to if you're just curious to look it up. It comes up in you see it. Well, for example, in differential equations, you might actually see the gamma function. So yeah, that's how the factorial behaves.
Thank you for that. Because
Sure.
yeah. And then does anybody else have any questions? Because the only other thing that I wanted to see was kind of a more simplified version of the shells, like a shell problem. Those were the ones that I don't know if I'm setting them up wrong or
Which
if
which section is this?
the shells were on the last test. So
Oh, okay.
yeah, so when I felt pretty confident going into it, and then I was putting the wrong number for when I was so when I'm finding the area, when I'm selecting what I'm going to use for the height and what I'm going to use for the width, I'm there's or maybe if you could just go over my work from the test and do that privately or something so that
Yeah, that might be a better way to do it.
yeah, so that I can, because it's like one number that I'm messing up when I'm doing it, and I just want to make sure that I have it right before we go to the final.
The final, yeah, okay. So why don't you do that? Do that on Ed discussion. Would you mind?
Okay, perfect. I can
Because
upload my work and
yeah,
then
I'd like because I'm getting almost no business there, and I'm wondering why suddenly it just kind of dried up there.
yeah.
Um, yeah, because I'm sure other people have similar questions. Yeah,
Okay.
since the test is passed now, it's okay for me to discuss the questions. So
Okay, then I'll just my scratch work is pretty detailed, so I'll just upload my scratch work onto there and then I can one of them I put it that it was rotating over the wrong axis, so I know how I got that one wrong. But I wrote the question down wrong when I was doing it. But the
okay,
other one, I don't know what I like which number I have wrong when I'm trying to set it up.
yeah,
I'm off.
I'd have those I have to take like a real line by line look at them. It's very hard for me to do it just by glancing at it. I have to literally work the problem from start to from the get go to see where you went wrong.
Yeah, I'll upload it into Edfinity. That works perfect because then
Well,
you
Ed
can,
discussions.
yeah, Ed discussions.
All right. Any last questions on the material for this sequences and series?
I think that not from me. Anyone else?
I think I'm okay.
I'm
Okay.
good too.
In that case, I'll go ahead and end this, and I'll post this in about an hour. And just can I give you a heads up? This is another crazy week for me, and I'm going to be. I will have some time where I'm available to answer emails and do ed discussions, but I'm also going to have some days where I'm going to be kind of absent. So by next Saturday or this Saturday, I should say, I should be back fully online. So be patient with me. I should have grades circulated probably first thing Sunday. That way you know what you have going into your last exam. So, alrighty. Well, again, thank you all for attending in 5, 4, 3, 2, 1.